Okay, let's move on to another problem or two from section 3.7. Again, we are optimizing. And let's work this problem. We're told that we want to find the point P on the line y equals 3x that is closest to the point 50, 0. What is that least distance between P and 50, 0? All right, so if we answer the first question, then we should be able to easily answer that second question. Let's first of all draw a picture of what this is asking for. I'm given the equation of a line, so maybe let's draw that line. This line has a y-intercept of 0, and it has a slope of 3, 1, so something like that. I'm not going to actually mark the axes because the slope will be the same whether I go up by a scale of 10s or 20s, as long as I mark my x-axis the same. The point 50, 0 is out here somewhere. This is the point 50, 0. Okay. This is the equation of the line y equals 3x, or this is the graph of the line y equals 3x. And I want to figure out what is the least or minimum distance between some point P on this line and that point, 50, 0. So I want to figure out, first of all, what is that point P? And then given that point P, what is this distance D? Maybe I'll call P XY just to give it coordinates. All right. So there is my picture. I need equations. How do I find the distance between between one point and another point? That would be the next question to ask, because this is specifically asking for a minimum distance. You remember from algebra that the distance B between 2 points is equal to the square root of the difference of the x coordinates. In this case, I have coordinates at 2 points. One is 50, 0. One I'm just calling x and y. So let's see. Those coordinates here, or the distance between the x coordinates here, would be, let's say, 50 minus x squared plus 0, which is the y value of that first coordinate, minus y squared, which I could write those in any order that I want. I don't have to write them 50 first because I'm squaring, but I'm choosing to. Okay. And then I have a second equation that I'm given up here. Y is equal to 3x, which I could consider my constraint equation. This is the constraint. So I have two equations, one with that thing I want to minimize and one that is a constraint. Now that I have those, I'm going to rewrite that first equation as a function of only one variable by taking this value for y, 3x, and I'm going to substitute it for y into this equation. So that gives me d, the thing I want to minimize, is equal to 50 minus x squared plus 0 minus 3x, all that is squared. Okay, I can simplify. This is equal to the square root of, I'm going to go ahead and square the 50 minus x. That gives me 2500 minus 2 times 50 times x, which is 100x plus x squared. And then 0 minus 3x squared is a positive 9x squared. I can combine like terms underneath. X squared plus x plus 9x squared is 10x squared minus 100x plus 2500. That is a distance equation, the distance between that point 50, 0 and any given point on the line y equals 3x. So I have a formula to work with. Now that I have that, well, let's figure out first of all, what is the domain of that formula or that equation? Part 4. The domain. Well, are there any restrictions on the coordinate of point P? That's what I need to ask myself. Well, x could be any positive real number. X could be any negative real number, because this line has a domain of all real numbers. I can use technically any point that I want for the x coordinate of P. So this actually has a domain of all real numbers, negative infinity to infinity. Okay. So I only have one possible thing to check if I want to figure out, well, what will minimize the distance value, what x coordinate. I need to look at critical points. So let's do that now. Let's write down that distance equation again, equal to the square root of 10x squared minus 100x plus 2500. And I'm going to find critical points. The derivative, this is a function of x, remember. So d prime of x is equal to, I have to use the chain rule to find the derivative of this. So I'm going to first of all start by rewriting this as 10x squared minus 100x plus 2500, all that raised to the 1/2 power. So I'm going to use chain rule to find the derivative. My outside function is square root of whatever's inside, so that's 1/2 times whatever's inside, 10x squared minus 100x plus 2500 raised to the power of negative 1/2. And then I'm going to multiply that by the derivative of what's inside, which is 20x minus 100. I'm going to rewrite that so it looks a little cleaner. This is equal to 20x minus 100 divided by 2 times the square root of 10x squared minus 100x plus 2500. Okay, so I've got that. Where's the derivative equal to 0? D prime of x is equal to 0. Well, that occurs whenever the top is equal to 0. It occurs when 20x minus 100 is equal to 0. So when 20x is equal to 100, or where x is equal to 5. Okay. I also probably should check where the denominator is undefined, or where the derivative, I should say, is undefined, where d prime of x is undefined. And I'm actually going to use Desmos to do this. So I'm going to bring that up. Let's go to desmos.com. con. Okay. I'm going to share my screen with you. I need to go to Desmos, which is right here. Okay. And that denominator is x, or 10x squared minus 100x plus 2500 to the power of 0.5. I'm going to zoom out. There we go. Okay, so it looks like the graph of my function. And you might notice that this graph never goes below the x-axis, so it's never equal to 0. And no matter how far I zoom out, it looks like it is defined everywhere. There are no jumps, there are no gaps, there are no places where it is cut off. Another way that I could check that is I could take this 1/2 power out. I could call this f of x is equal to that function. And I could say, well, where is f of x equal to 0? It does not appear that there are any locations because no solutions show up on Desmos. I can also check where is f of x less than 0. It appears that there are no such locations for that either. Therefore, there are no locations where this derivative is undefined. Okay? So let's go back to that problem. We're here. Oops. And we said that the distance, or the derivative, d prime, is equal to 20x minus 100 over the square root of 10x squared minus 100x plus 2500. And we just said, I'm looking for locations where that derivative d prime is equal to 0, or the derivative d prime does not exist. I don't get any for this criteria, but I did find that for that, if x is equal to 5, then I have a critical number. Now that I have that, I need to figure out, does that actually give me a minimum? So that is step 6. This was step 5. The minimum of this, well, if I use first derivative test, say this is 5, and let's test in that derivative function, let's maybe test 0 for x, and let's maybe test 100 for y, or for x values greater than 5. Those will make our calculations easier. D prime of 0 is equal to 20 times 0 minus 100 over the square root of 10 times 0 squared minus 100 times 0 plus 2500. Put that in our calculator. That's equal to, the top is negative 100. The bottom is square root of 2500, which is 50. So that's equal to negative 2, which is less than 0, and that's all that we really care about. So it's negative here. you could similarly say that d prime of 100 is equal to, I won't go through the calculations, but it's equal to positive 2, which is greater than 0. That's all that I care about. That's positive. So the graph is decreasing in this interval. It is increasing in that interval. This indeed does give us the location of a minimum. So what's that say? That says that when x is 5, when x is equal to 5 and y is equal to, well, remember y is 3 times x, so 3 times 5 is 15. The coordinate 5, 15 gives us the minimum distance on the line y equals 3x from the point 0, 50. Okay, so that's the coordinate of the point. If I want to find the distance between that point and 0, 50, then I can use the distance formula. Distance is equal to the square root of, what is it, 50 minus 5 squared plus 0 minus 15 squared is equal to whatever that number is. I'm not going to actually calculate it. I'm going to trust that you know how to do that. But if I know the coordinate of that minimum distance point, then I can certainly find the minimum distance. And I think we'll stop there.